Here we go. Okay, so in case any of you missed that, I'm Owen O'Malley. I'm going to be talking about optimizing Hive queries. The person from Intel who was going to give a talk on benchmarking Hadoop couldn't make it today, and so they asked me to give my talk today and as well as tomorrow afternoon. So just making sure everyone's in the right talk. So who am I? Actually, ironically, I probably could give a talk on benchmarking Hadoop. I've been working on Hive, in particular working with customers. I previously worked on Hadoop MapReduce. I've also worked on Hadoop security. I was the architect for both of those. I was just telling people in the audience earlier, I've been much better about getting out of MapReduce because I actually found someone to replace me. As security, I haven't found someone to replace myself yet, so I've been less successful for getting out of that. But I've been working on Hadoop since the beginning. I actually was the first committer added to Hadoop, and my first patch went in before Hadoop was actually called Hadoop. On the Apache side, I'm on the Hadoop PMC, I'm on the Tez, which is a new project, Ambari, Giraffe PMCs. I'm the mentor actually for a whole long list of projects, but those are 3 of them, and I'm an Apache member. So what am I going to talk about today? When you talk about optimizing Hive queries, there were a whole set of things I wanted to talk about, and then I realized, oh, I've only got 40 minutes. I don't have 3 days to talk to you guys, give you lab assignments, and so I had to pick and choose. So I decided I wanted to talk about the data layout, the data format, how to set up, how to think about joins, what joins you've got available for yourself, and how to debug when your performance isn't working. So data layout is all about location. When you start using Hive, you need to start asking yourself the fundamental questions. Okay, what kind of data am I going to have? What kind of queries am I going to have? And you need to think about that much more rigorously than you need to in a standard traditional database, because your access to the data is going to vary widely depending on how it's laid out. And so you need to kind of think about these ahead of time. You can change your mind, of course, but you want to think about what are my use cases? What do I need to do with this data? And because that impacts a lot of your layout decisions. Now, that's pretty different from where we started. With Hadoop MapReduce, people are like, oh, it doesn't matter, it takes unstructured data, you don't need to think about it, just throw it into Hadoop and worry about it later. Well, guess what? We actually do care about the layout, especially in Hive, but all the projects make use of the layout. And so if you get the layout right, your performance will be much better. You need to think about, how am I going to access this data? What data is going to be accessed together, right? If you do particular joins of individual tables often, you want to lay them out in related ways so that it's easier to do those joins. If you don't, it'll still work, but it'll be much slower. And so it helps a lot if you think about that ahead of time. You also need to think about how much data you have, okay? I've seen all ranges of it. Everything from relatively small, although in those cases, they probably shouldn't be in Hadoop, but they usually are in Hadoop because they expect to grow large. And that's the other piece, is you want to think about, okay, not how big is my ingest rate now, but what's my growth year over year, right? If you've got a terabyte a day of data coming in now, that's great, right? That's a great size for Hadoop to deal with. If it's growing 3x year over year, then you really need to think about, how am I going to deal with this next year? By the way, I guess I should have said, this is a really small audience, so feel free to ask questions as we go, and we can take them. And finally, you need to think about, how do you get the data, right? How does the data come into your system? With Hive, definitely the queries are much easier to deal with than doing updates. Doing updates takes some effort. So you need to think about, okay, I'm getting data in every half hour, every hour, right? You need to think about where that data is coming from. Again, typically the data is coming in from either logs or it's coming in, I've seen customers that have Oracle databases that serve the real-time traffic, and then once an hour they get a dump off of the Oracle database, and that feeds into Hive. And if you're doing ingest like that, then you want to think about, okay, I can only override at the partition level, so I need to lay out the data so that I can update an hour's worth of data. Now, Hadoop and Hive are definitely in the stack. So you need to understand some of the characteristics of HDFS before you understand why Hive made some of the decisions it did. HDFS does really great at a lot of things, right? It gives you high aggregate bandwidth to your data, right? If you look at a filer, for instance, it does really great at storing files and keeping them there, and you can store a lot of things there, but you're completely limited by how much access you have to that data. You can't get a lot of concurrent bandwidth to the system. With Hadoop, that system provides that access. You can get the data there very easily. It provides extremely high scalability. You can keep adding new machines. The biggest clusters I know of are up to 100 petabytes of storage, okay? You can dump data in and never delete it. That's really awesome. It's self-healing, right? At that scale, if you lose a handful of servers every day. You don't care, it heals itself. And it's relatively simple to administer, but it has limitations. You can't modify existing files. The HDFS guys will say, oh, but we can append now. It's like, yeah, but you can't modify them. And actually, Hive doesn't even take advantage of the append onto current files because of the fact that Hive needs to maintain backwards compatibility with very old Hadoops because that's what Facebook uses. They are running a fork of Hadoop that was based off of 20.1, so we don't have a append that we can use across the stack. You also only get a single writer, so that means that each file can only be written to by one process at once. And there's a heavy bias for large files. You want to keep your files relatively big. Again, it'll work with smaller files. It won't waste disk space, but your name node will start having issues as you scale up. Okay, so if we look at Hive's layout, the top level choice is partitions. This provides a directory where all the rows underneath that directory have a single value for your partition column. So the most often used partition is the date column. And that provides both the mechanism for how you update it, right? You can update either a whole table or you can update a partition. But, so it's important for that, right? You need to lay it out that way. But the other thing where it matters is because your queries can just do partition pruning and they throw away all the other partitions and won't even look at them. So if, for example, most of your queries are date ranges, you're going to probably want to partition on date. The next level one is bucketing. That's where all of the keys that you pick for bucketing get hashed, and it'll pick that bucket, and the bucket corresponds to a file in HDFS. And that's primarily used for sampling and also for particular joins where you want to look at all the related values. It also controls how much write parallelism you can have. Because in Hive, the number of writers you can have writing the results of an update query, or rather, more precisely, insert overwrite, is controlled by the number of buckets. So if you have a table with 128 buckets, you're going to have 128 writers into that table anytime you do a query that does insert overwrite. Does that make sense? So you don't want to pick a number that's too low because then you won't be able to have enough writers to write it fast enough. And finally, there's the sort order. The sort order controls the order that the data is written into the file. So if we look at what this looks like in HDFS, you've got your warehouse directory, then there's a database directory, there's a directory for the table, and underneath there, you've got your partitions. You can have either single level or multiple level of partitions. And those have names like part, equals, and then the value. Then the bucketing, and the bucketing is just a file, and so typically you'll see the names like 6 zeros, underscore, and 0. And those are coming out, the first 6 numbers are the bucket number, and the last 0 you can ignore mostly because that's which attempt actually succeeded to write the file. And then the sort is the order within the file. So one of the things that you notice when you start running Hive queries is that if you have a lot of partitions, it runs really slow, especially in the setup of the query. So you're much better off if you can get by with 1,000 partitions rather than 10,000. Although I've seen tables with 100,000, and that's pretty unfortunate. It just takes a lot of time to get those working. And anytime I've seen nested partitions, it usually ends up being a mistake because you end up with a lot more partitions than you're thinking about. Because if you've got 50 choices for this partition and 1,000 choices for the second one, then you've really got 50,000 by the time you're done multiplying those out. And then you need to think about the number of buckets. The goal here is you really want to keep the file size reasonably big. You want 200 to 500 MB for the files. And you've got the number of buckets times the number of partitions in your table. But so let's say if you've got a terabyte a day and you've chosen 100 partitions, that means that each of the files is only going to be 10 megabytes. That's too small, right? You want it to be bigger than that. Oh, sorry, no, that's gigabytes. That's still fine. But you want to calculate the size and keep your files large enough. You also want to remember that your name node can store somewhere in the order of 50 to 70 million files. So you don't want to cause your name node grief by making it too large. And you will, for the most part, end up with the number of buckets times the number of partitions in your file system for each table. You also want to lay out related tables in the same way. So if you're doing joins between a table that has customer information and the sales information, then maybe you sort the sales information by, or maybe you partition by the date, but then you partition and bucket by the customer ID so that you can do joins much easier. Obviously, if partitions are the same, then you can match up individual partitions and Hive will go faster. Now, one of the pieces that is interesting about Hadoop is that unlike most databases that really suggest normalization, I guess I should define normalization. Normalization is where your database layout has a single table for each kind of information. So you've got a table about your customers and a table about your sales, a table about returns, and a table about inventory. And there's a separate table, and you're always doing joins. That has a lot of good properties, but especially in Hadoop, it's typically slow to query. We're working on fixing that. We're doing a lot of work, actually, to make star schema joins go faster. But denormalized data is actually much, much faster to deal with. So especially if you're doing lots of queries on the denormalized data, you're much better off denormalizing it when you're loading because you write it once and then you join and then you read it many, many times. It has the additional benefit that you get a snapshot in time, right? If you have just a customer table and a sales table, then the customer table is always his current information, right? You don't have any updates as he moves because you just update the customer table. But if you have the sales information include the customer ID or customer information, not just the ID, the whole information, then you get the information as of that point of the sale. So you actually get some additional capability out of that. Yeah, actually, that actually makes a lot of sense and can make a lot of queries much, much faster. Again, it depends on the volumes of data you've got to ingest, but definitely denormalization is something to keep in mind as a very good strategy. And I've seen it be used very successfully in a lot of companies. Correct. Hive over HBase definitely works. I haven't used it as much, and the performance is definitely not where it needs to be. So it definitely needs some loving attention on the development side to really make that work. For some customers, it's no doubt the right call because they have a high level of updates, but the performance there is definitely suboptimal. I definitely recommend using HDFS over HBase as long as you don't have updates that are going to overwhelm you. Okay, so data format. Hive breaks the data format problem into two pieces. The goal, of course, was to be able to read data in your format and ingest things that way, right? It's very powerful that Hive can just say, load this whole data file, and it doesn't have to rewrite it. It can interpret a text file or whatever as a table. And actually, almost everyone does that, and they use, that's how you load data into Hive, is you have two tables, a staging table and your final table. The staging table will have the text. You put the text file there, you load it up, then you copy it from the staging table into the real table, and it'll change the format as part of that copy. So the survey controls how the record is broken down into pieces, how it divides out the columns, how it converts the columns. Sorry, survey stands for serialization, deserialization. And so it really is the thing that controls how the format of the serialization. How is it going from bytes into the value that represents the column? It also deals with how do you separate the different columns apart from each other. Then you have the input-output format, which is also often called the file format, because that's how the files are actually stored. The primary choices for the file format are text, sequence file, RCFile, and a new file format that I'm working on now called ORC. ORC is committed into Hive and Hive trunk, and it'll be coming out in version 11. So text format. Text format is where people almost always get started. Of course, there the survey is absolutely critical because it needs to have information about how to split things apart. The default survey defaults to control A's between columns. So if you have control A's in your data, you're good to go. If you have something else, then you need to at least control the survey parameters to make the separator what you want it to be. There's also other surveys. There's a JSON survey that lets you pull apart JSON files. I've used that one before. There's a CSV one that's on GitHub. But it's important to use those because you need to control how your data goes from bytes in the file into actual records. The problem with text, which is why when you see benchmarks against Hive, 99% of the time it's with text file, because parsing the text file is actually slow. It just takes a lot more time than you'd like. Furthermore, when text files are compressed, then they can't be split because gzip, it starts at the top and keeps going all the way down. And so if MapReduce picks a spot in the middle, it can't figure out how to get the compression resynchronized so that you can't start in the middle of a file. That can be, LZO, even with LZO, you have to use the Twitter stuff to make an index. LZO itself isn't splittable. So yeah, you can fudge it. Actually, I've used the LZO trick also. There are actually tricks you can play with gzip too, but they're much less friendly even than the LZO trick. But that's definitely something to think about because if you've got this, multiple gigabytes of text file compressed, then you'll end up with this huge map task that runs and then takes forever to process. And of course, you need to read and decompress all of the fields. So if you look at sequence file, this is where MapReduce, the traditional MapReduce binary format, you mostly don't want to use this with Hive. It was set up for keys and values as classes, which worked great for Java MapReduce. It doesn't work so well for Hive. And actually, Hive, when it's using sequence files, only stores the row as the value. It doesn't use the key at all. This one's splittable, even if it's compressed. It's on 1 megabyte boundaries. Of course, it gets a whole row, so it's whatever over 1 megabyte is a complete set of rows. But you still need to read and decompress all the fields. So some of the guys at Facebook saw this and said, okay, well, we can do better. We can take some of this literature about row columnar stuff, and we can split the sequence files up so that we store each column by itself so that you can read just the columns that you need for a particular query. Works great. It also gives you better compression because if you've got a string of integers, then those are going to be more related to each other and therefore compress better than if you have it mixed in with all the other columns. But the RC file, because it still goes through the Serde, stores all the columns as binary blobs. That means that there's no information in the file about, oh, those were integers, or oh, those were strings. It just says, okay, here's 4 bytes, and it actually records using an integer, oh, every value in here is 4 bytes, and it stores the whole 4 bytes there. Fortunately, it does run length encoding on the length, so it gets those smaller, but it can't do run length encoding on the values themselves. It has larger blocks, 4 megabyte by default. Although 4 megabytes sounds like a pretty big block size, in Hadoop land it's not, especially if you've got 100 columns, then each of those 100 columns is 40K in a 4 megabyte. So 40K is a really small chunk of data to be reading. Unfortunately, they copied the part of sequence file where to find the split, they pick a location and then start searching byte by byte, and so they still do that. So we looked at the issues and looked at more of the research, and then I started working on the optimized row columnar format, which I called ORC. The columns are all stored separately. So RCFile, it just takes the top level columns and stores them separately. ORC takes them all the way down. It breaks everything down to primitive types. So if you've got structs, lists, maps in your fields, it doesn't store them as one contiguous blob. It stores them down to the primitives. It uses type-specific encoders, right? It knows this is an int, so I'm going to use variable width encoding for the integers. So if it's a small value, it uses 1 byte. If it's a huge value, it will use all 4 of the bytes. It uses run length encoding. So if your row has 1 million zeros in it, it'll be very small. it also uses dictionaries for strings, so that if you have a low cardinality column, say it's the state that, or the province that the address is in, then it'll keep the dictionary with just the one for each province it's seen, and then encode it like an integer column. So it'll just have an integer reference off to it. It has a lightweight index where we store the min and max for each of the columns. That lets us skip over whole sets of rows. So let's say I'm looking for people that are in the state of California. If it's sorted by state, then because every 10,000 rows I've got the min and max for the state, I can just say, oh, it's clearly California, none of the records in this batch of 10,000 rows are in California, so I don't need to read them at all. I can just skip over them and go to the next set of 10,000 rows. So I can just effectively get the results of having a secondary index without having more partitions. It has much larger blocks. I made 256 MB the default, but because scanning over 256 MB would have been really slow, I made an index at the bottom so that you can jump right to where the blocks start. If you look at the file format, it's divided up into stripes, with the green being the index data, the blue being the row data, and the red being the stripe footers. You can see that the index is broken down by columns, just like the data is. So if you don't need the indexes, you can just read the data. If you do need the indexes, you can read the columns you need and skip over things. The file footer has things like the overall, where the stripes start, and the types that are involved. In terms of benchmarks, I took some from TPCDS. On the left side, you can see the files encoded in their native text format. I normalize this to one. The blue and the red are two different files out of the benchmark. Then if you look at RCFile, they've come down to about 60%. If you look at the ORC, they've come down to like 20%. Then if you turn on compression, the next three are with compression. So gzip comes down to, well, they're pretty different at that point, but let's say 30%. RCFile compressed with zlib is down to 20%, and ORC gets even smaller. And yeah, the blue line is actually there for that last one. It's just that file compresses insanely well. And so it's so small you can't see it. You also need to think about your compression. There's LZO or snappy. Those are fast, but leave lots to be gained. So if it's a temporary file, those are probably the right choice because they cut down on the I/O and don't take that much CPU to compute. If you are storing it for longer term or you're going to be reading it more often, then you should probably be using the zlib or default compression. Those are the same. Just two different names for the same thing. It's slow and does a very good job of compressing your data. Okay, now I wanted to look at joins. This is where the fact that I'm an architect rather than a sales guy comes through. Hive basically assumes either you know everything about Hive, everything about MapReduce, everything about HDFS, or you know nothing. And they're going to make completely safe assumptions for you. So Hive has all these knobs that let you turn on all kinds of crazy, wonderful optimizations. But if you don't know, it won't enable them because it assumes you don't know anything. So those are your two choices. Either you're a Hive newbie or you're a Hive developer. And the default option, on the other hand, always works. It always gets the job done. It'll just go very slowly, which is good. It's much better than a lot of systems that I've looked at where if you run with the default options, you hit some point and then it runs out of memory and crashes your whole query and you have to start all over again. That's a much worse behavior. Always finishing is good, and so I like that. But the expert behaviors are in fact there, And you can get those behaviors by turning them on. Part of our work, because we're trying to actually get people to get better performance, is in fact working on improving those heuristics so that the right things happen by default. Okay, so the default choice is the shuffle join. It always works. It's pretty much the worst case scenario in terms of performance, but you can sort any size. I've sorted a petabyte using the default, the shuffle. And each process reads part of one of the tables, buckets and sorts it on the join key, and then sends one bucket to each reduce. Easy, straightforward, works every time. Map join works really well if one table is small. So it's like a dimension table, right? So if you're joining your sales data versus your customer data, you probably don't have that many customers. Although, to be fair, I have seen dimension tables that were so big they didn't fit in RAM. One customer table I saw was like 760 gig. I was like, okay. Billions of customers. I wish I had that problem. So the process reads, all of them read the entire small table into memory, keep it in a hash table, streams through the big table, although they only read through their part, and then they join every record with that they read from the hash table. It's fast, but it requires you to have enough memory to do it. SMB, sort, merge, bucket join. If they're sorted the same and bucketed the same, but not necessarily partitioned the same, then you can join them. Although I will warn you that there were challenges in the current version, but they're getting fixed now. So you have to try it out and play with it. But what this does is it'll read from each side that it's joining, and because they're sorted and bucketed the same, it will take the first one from each and read whichever one's less. So it's really efficient if it's applicable. Okay, actually I'm running out of time. Okay, so which of these queries do you think is faster? There's select count distinct of some column from a table, or there's select count star from select distinct column of the table. So they come up with the same answer, right? It's a number. Which one do you guys think is faster? You'd expect the first one. It should be faster. These are what the graphs look like. So if you look at a MapReduce, the first one has a bunch of mappers and they all send their reduce to an output, to the reducer. And the second one has got mappers that write to the reducers, they write to HDFS, they run the mappers, and then it runs to the reducers. So now it definitely looks like the left one should be faster, right? It's way less work that you're doing. But no, the second one's faster by an order of magnitude. And that's really unfortunate. So the first one, each map is getting taking its distinct values and sending it to the reduce, but there's one reduce. That one reduce is collecting all the values for that column. So it can get completely overloaded. In the second case, it does the maps split into reduces, but then it sends them to a whole set of reduces that can be across the cluster. And then those reduces generate a list, and then the second MapReduce job just counts the values. And singleton reduces almost always bad, unless it's very small data. But in this case, you have small output, but you don't have small input to the reduce. So how are you supposed to know about that, right? If you just look at the queries, you'd say, oh, the second one should be way longer than the first one. And the answer is there's a tool that helps you called explain. Hive doesn't tell you what's wrong. You have to ask. Hive just says, oh, you finished. You did good. But sometimes you have to look deeper and find out what's going on. So the explain tool gives you the query plan. It gives you like what filters on the inputs there are. It shows you the number of jobs. It shows you the number of maps and reduces, what the jobs are sorting by, and what directories they're reading or writing. this is good stuff. And everyone who's using Hive should start using the explain tool. Unfortunately, the output of the explain tool is confusing. Again, it assumes that you're a Hive developer. We need to fix this, but it takes practice to understand it. And it's missing some of the pieces, like it doesn't talk about partition pruning, which makes a huge difference. But I definitely recommend that you start using it, and you know, if you have suggestions for how to make it better, definitely file JIRAs and even better submit code back. But it's one of the things that needs to get better because people need to understand what's going wrong. Sometimes you need to also run the query because the tool's not clear enough. But then you need to pay attention and look at what the job conf and job history files are saying. Now, one of the other issues that can become apparent when you start running these tools is the concept of skew. Almost every real data set has skew. Yeah, someone can read faster than I was talking. So a user was complaining that their job was running slow. They had 100 reduces. 90 of them finished really fast. The other 2 were taking forever. He's like, what's going wrong? Well, his key was a Boolean. Reduces are going to take one value and hash it. So if there's a Boolean, there's only 2 values that actually, he was actually lucky. If he'd been unlucky, there would have been 1 reduce that was getting everything. So he was getting lucky, really, but yeah. Pay attention to skew, it matters a lot. I wanted to talk about one more tool that's useful for debugging things. If you use Ambari, which is the installer at Apache for installing and managing Hadoop, there's some metrics and metrics dashboards that you can use there, which are Gangly and Nagios. Those are really useful for keeping track of your cluster. But there's a new feature called root cause analysis. It basically processes the MapReduce job logs as they run and displays the timing of each part. So here you can see, okay, my query had 5 jobs. The first one took a long time, and then they took successively shorter pieces. The bottom shows like the breakdown of what the tasks were doing. So you can look at these and start getting more and more information about what's going on in terms of your queries. This is another one out of root cause analysis. It shows the time scale along the bottom is a timeline when the tasks were launched. The size up is how long it took to run, and the size of the dot is how much data it processed. The green ones are maps and the blue ones are reduces. And so you can see that the ones that were outliers, right? Like clearly this is a skew problem because that big one that took forever has a lot more data than the smaller ones. So these are the kind of tools that can make a lot of difference. Okay, that's what I had, and I've got like a minute and a half, so. Yes. Uh-huh. Yes, I should have actually had examples of how you select each of how you put each of the things. But yeah, you're definitely right that if you have multiple tables joining, if it's just 2 ways, it doesn't really matter that much. But if you have multiple ways, then you want the big table last. Again, we're working on the heuristics to try and make that less important. Actually, the Hive trunk, that optimization has gone in so that it doesn't matter which order you put where. Yes. Absolutely. You need, unlike traditional SQLs, You need to, again, use the explain tool to really see where the filter is applying. But her point is that the clauses in the join clause take precedence as it's being joined, or the input to it. And if you put in the where clause, the result of the join is then filtered. So if they're a very selective filter, you absolutely want it to be in the join rather than in the where clause. Yeah. Mm-hmm. Hive already has subqueries. Not in the in clause. Unfortunately, that was on the roadmap, but it got slid out, so it's probably going to go into Hive 12 and not Hive 11. Hive 11 is coming sooner than that work will get done. Hive has been releasing roughly quarterly. Any more questions? Okay, well, thank you very much.